In this lecture, we're going to finally try out some examples of exploratory data analysis. We're going to use a computer to do it. Specifically, we're going to work in R inside of a Jupyter notebook. And we're going to use this mode of delivery quite a lot throughout the other lectures. So what you'll see is I'll switch back and forth between a bunch of things that are done on my tablet in modes in a way that you may have seen me do in other lectures already. And on the other hand, I'll switch to a screenshot on my computer where you'll see me executing a bunch of lines of R code. And then you'll see what comes out of them, and then we'll discuss each line as we go. I hope you like this method because lots of the future lectures that combine both mathematics and computational stuff will work in a similar way. And more importantly, I guess, I hope that you learn some new things about the exploratory data analysis tools that we try out today. All right, let's get started. Today we're going to be going back and forth between writing in this whiteboard environment here and this other environment which I'll jump to now, which is a Jupyter notebook, which is where I'll run my R code. I'm not sure if most of you will have used Jupyter before, but it's a thing that runs in your web browser. I like it particularly for teaching. It might not necessarily be the best environment for development. Certainly the folks here in the stats division use RStudio much more often than Jupyter, but I find Jupyter works quite well for teaching, so I'll be using it for our lectures. Okay, so the first thing I'm going to do is just a few little basic examples, probably of things you already know how to do, and then we'll get on to the new content. We're going to be looking entirely at the data set, almost. Actually, at the end we'll use some other data, but we're mostly going to be looking at the data set Sandstone, the Sandstone data set that has a bunch of properties, measured properties of different types of sandstone. This is the same data set that you used in your first practical of this week, the first computing practical. So I'll load that up, and the data set's small enough that you can just show it and look at it all. I'll just remark, though, that as you watch these lectures where I'm working on code, it's probably a good idea to open up RStudio or Jupyter or whatever your favorite R environment is, and try to run these commands on your own and make sure that you're following along how they work. I won't always say exactly what every single line is doing. So, for example, here I should have mentioned that this path is to the file on my computer, and your path is probably different. So that this exact line won't work for you. You'll have to put your path in here to the file. Okay, so I'll load in that file and we'll take a look at it. And just to kind of I really just want to look at its dimensions. So it's got 5 columns of different properties or features of sandstone and 40 rows. And there's no missing entries. And that's about it. That's all I want to look at right now. And we'll maybe reflect back on this later when we want to see if we can understand certain things that we're seeing. The first thing I'm going to do with it is just show you how to plot one variable versus another, just a scatter plot. And this is something you've probably done before, but if not, you certainly should see it. And this first line here is just about me setting some dimensions for the output that I like. There are lots of different ways to tweak the plots. I'm not going to go through them all, but this is just, I'll once in a while show one. This is one here. I'm going to plot on the vertical axis, the formation column, which is column 4. And on the horizontal axis, I'm going to put column 5, which is polarization. And so we'll just do that here. I'll execute this block. There you go. And it's plotted these things as little circles. The graph is a little bit big for my screen here, but I hope you can see it. And so that's just a basic scatter plot of those two, one variable versus another. Formation and polarization. And we're able to use those names because we stored the names in the data file when we loaded it. We kept its header. I think that was how that came about. So that's just how you do a basic scatter plot. The next thing I'll add is, I think this is kind of cool. It's old school, I think. But I think it's kind of a neat trick from old school land, which is something called a rug plot, which is similar. It's just a scatter plot, but on the axes, there are little tick marks next to the value associated with every different point. So like this point here would cause a tick mark to appear here, as well as a tick mark to appear down here. And this point would make a tick mark here and a tick mark here. And then, so you'll get a bunch of tick marks along here and a bunch along here. And because of that, they look kind of like a little carpet or rug. And so it's called a rug plot. I think it's pretty old school, but I also think it's kind of cool. So there you go. And you can apply the rug to only one side or another. But I think this is kind of neat. It's a quick way to get a feeling of where are the points bunched up on the two different axes. You can, of course, also see this just by looking at the plot. So that's maybe why it's not so heavily used anymore. But I think it's kind of cool. Okay, and then the last things I want to introduce before we move on to kind of new tools is one that we actually used in the last lecture. We looked at a series of different scatter plots. The family of scatter plots, all the different pairs of columns. So sometimes those are called pairs plot or pairs plots. And so I'll run that and you'll see it. We've already seen the output. We just never, we didn't produce it. There you go. And so you've seen this before. So this box, for example, is a plot of conductivity compared against formation. And I can't remember which one goes on which axis, but you should be able to figure that out relatively quickly. We should be able to check it. So let's see. So the vertical axis here goes from 5 to 20. I bet that's for formation. And conductivity goes from 0.01 to 0.2. So 5 to 20 is probably formation. So let's go back up here and look. Formation, yeah, it looks like 5 to 20 fits better for that than for, what was the other one? Conductivity or polarization? Polarization, yeah. But yeah, so that, oh, sorry, I was looking at this spot, conductivity, yeah. So this axis goes along with formation. Anyways, you can decode this relatively easily. I wanted to remark on a couple of things. So first of all, this is a nice thing to do when you have a relatively small data set like we have now. If you have a big one, it's not such a great idea because what happens is all these plots just get kind of crowded and you can't really see very much. And they're so tiny because there are so many of them. So this has somewhat limited utility, only kind of for use with modest sized data sets. If you ever make any plot that you think you might want to use, like in a report or in some other formal environment like that, you shouldn't ever take a screenshot of your R window and try to use that. That's a bad idea. It'll make a graphics file, which is pretty poorly encoded when it comes to putting it into a formal document. So you don't want to do that. You want to use some kind of command similar to what I've done here. And this is going to make that same plot. But it's going to, instead of outputting it to the screen, it's going to output it to a file in the file that I've named here. So I'll just run this. You won't see a new plot appear, but it will produce a file on my desktop, which I should be able to grab over here. This guy. And you'll see what I mean. It makes a nice clean PDF, which can be rescaled without losing any kind of quality, right? So you can zoom in on it and you don't get a big pixelated mess. You get a clean representation of what's there. And this just says because of the way that the image is encoded. Okay, so yeah, so now I want to do a little bit of three-dimensional work. I don't know that R is really such a great environment for this, at least not in the base R graphics, which is what we're using here. But nevertheless, we'll kind of show you how they work. So I'm going to use a library Scatterplot 3D, which you'll have to install before you can load it with this command. And I'm going to make a data set that's just the first 3 columns of the SPS data set, the main sandstone data set that we imported. And then we're going to make 4 different plots arranged on a 2x2 grid. And each one is just this data set, but viewed from a different angle. And so we'll run this here. And I think you could probably get the idea for why this is not necessarily the best. R is maybe, or at least this default output is not necessarily the best. You can see the numbers are all overlapping with each other here, which is pretty bad. But nevertheless, it is something you can do to get an impression of things. You also should be able to do an interactive version of this. And it doesn't work for me in my environment in Jupyter. I am able to make a plot using this other thing. So this is RGL, I think, is R graphics library. you can do this, and it should pop up a interactive 3-dimensional plot that you can twirl around with your mouse. You'll see it doesn't work on mine. I think it will produce a plot. I think it's opening up, yeah. So it's opening up some kind of X Windows server, old school thing. And I should be able to kind of twirl this thing around, like by grabbing it and moving it, but it doesn't work for some reason on my machine. And I think that's either because I'm using a Mac, or because I'm using Jupyter, or maybe both. I think if you're using RStudio, this would actually work for you. And then you can't you can't even close it in the normal way. Like, it doesn't do anything. You have to close it from the command line here, like that. And you'll see that now it's gone. Okay, so the next thing I want to introduce is something called a bivariate box plot. And I think I'm going to make it first, and then I'll describe it, and then we'll come back and look at it again. So it's like it says, it's bivariate, right? And so it's got only 2 variables that are going to show up in the plot. And it really only has information about those 2 variables. I'm using several libraries here. This is, I think, actually also not just for right now, but for later on in the notebook that I'll need those libraries. And then I'll just make this box plot with the 2 different columns, so column 2 and column 1. Yeah, and so I'll go ahead and make that, and then we'll discuss it. So it looks like this. It's supposed to remind you a little bit of a box plot, but again, it's bivariate. Like on box plots, the horizontal axis, or well, it depends on how you've laid it out, but usually it's a horizontal axis has no meaning. Or at least one of the axes will have no meaning. In this case, both axes have some meaning, and you can see there are some ellipses here that are enclosing the data set, the data points. And I'm going to jump over to my whiteboard area and kind of describe what we're seeing here. Oh, where did it go? There we are. Okay, so what we're doing today is a bunch of examples of exploratory data analysis tools in R. This is the focus of today's lecture. So I'll put that big box around that. And the first thing that we're going to discuss is just this bivariate box plot. I mean, the first thing I'm going to write notes on about. So bivariate box plot. Box plot is probably an unfortunate term here because, as you can see, it's not using boxes. It's using sort of elliptical shaped things. But nevertheless, that's what we call it. And so what you get is a pair of ellipses the axes, so I don't know if you're familiar with the terminology for ellipses, so I'll just introduce some terminology here. So here are the 2 variates. I'll call them like x1 for column 1 and column 2 here from the matrix X. And so you've got your data is kind of all over the place. Maybe I'll use green here for that. This looks roughly how it did in the picture, I think. And you get these sort of ellipses. So one of them is in here like this. And I think the other one was dashed. Like that. They both have the same, their axes, they're what's called semi-major and semi-minor, or major and minor axes are aligned with each other. So those axes are like here and here. And those axes are lines of best fit for the data. I believe fitting only the data within the ellipses, but I could be off about that. Where you're minimizing the squared error either on the vertical axis or on the horizontal axis. So that's why you get 2 different lines there. And so that sets the kind of rotation or orientation of the ellipse. And then the scale, or like the radius of the ellipse, is controlled in 2 different ways. So first of all, these things have names. So this external one is called the fence. These names are not really so important, but and the interior one is called the hinge. I'm not sure what are the origins of these names, but so the hinge is of a size that will include half the data points inside it. Contains half the data set. And the fence, I believe that the fence size is something that you can kind of modify in the command, but the fence essentially is what's used to determine or define outliers. Or maybe like points that you're kind of curious about and want to maybe consider not using, or I don't know. So like these guys would then be outliers because they're outside the fence. And you can set, I believe, your own rules for where the fence goes, for how big that second ellipse is. Yeah, so that's the bivariate box plot. And you can see roughly what's going on here is it's just trying to show you kind of what the distribution might look like for these data points, which is similar to what the box plot is doing in one dimension. Okay, the next thing I'm going to introduce is something called a bag plot. And the bag plot is much more complicated. So these tools, I think you'll find these tools to be kind of, they come in different flavors, sort of. Some are super simple or relatively simple to understand. And maybe you would then find utility or a lot of use for them. Or then some of them are a little more elaborate. And for me personally, I don't like to use tools if I don't really fully understand them. And I think the bag plot for me might be kind of in that category. It's a much more elaborate or kind of ambitious tool. So maybe it's super powerful if you get comfortable with it. But I think it's a more complicated thing. So the bag plot, I'll just say something about it before we look at one. It's similar. So it's similar to bivariate box plots. So it's sort of like, I'll say it's like a bivariate box plot. But the bivariate box plot only contains information about the two different variates shown, so the two columns of the matrix that you were interested in, of the data matrix. But in the case of the bag plot, it contains information about all the variates, but with info from all p variates. So in our case, p is 5. So that's a 5-dimensional space looking at all those variates. So somehow I'm going to look at something in 2 dimensions for the 2 variates that'll make up the bivariate aspect of the box plot. But there's information in the plot that comes from the full 5-dimensional space that's somehow projected down. And that information is a little bit complicated. So let me go ahead and make it. And then we'll discuss what we're seeing. So we'll go over here. So the commands for doing it are simple. I'm going to make 2 plots, so that's why you see this thing here. One is going to be just a scatter plot, just the bivariate box plot, the one we've seen up here. So I'm just going to reproduce that again. And then the next one is the bag plot, and it uses this thing, another plotting library. To make the bag plot, and it looks like you do it like this. So there's other ways to run it as well, of course. And so we'll make it and kind of look, and what you'll see here, so both of these, so the axes are not labeled properly here. This is permeability, and this is porosity. And the scales are right? So this is 15, 0 is a little lower here. So this should be sort of higher up if you're going to compare it. This ellipse should be kind of dragged downward somewhat. But in any case, you can kind of see that these are the same 2 set of axes. And over on the right is the bag plot. And the bag plot is much richer in information because it really is informed by things on the full higher dimensional space. So the first thing I'm going to try to explain with the bag plot is just this, its center over here. Whereas this guy, I think the center is what you call the centroid or something. It's a relatively simple concept that you can determine, like that you can define, but I won't get into it. But this one, its center is defined in some weird way, and so I'm going to jump to the other screen here and say kind of what that is. So first of all, the center. So the center, which we marked with a star. Well, actually, lots of things use, I'll say about the center in a second, but lots of things. So it uses this concept called Tuki Depth. Tuki, the person, and then depth. Maybe I'm pronouncing that poorly. Depth. So like deepness. Uses Tuki Depth. And Tuki Depth is a weird, sort of, to me, it's a little bit of a funny concept, and it looks like this. So let's suppose, for example, that the P is just equal 3, right? Which is a little bit of a simple case, right? So we just have 3 variates. In that case, let's suppose that we draw the different axes for the variates here. And I'll just sort of sketch where the data is, kind of, just pretend. So pretend we have this data set that kind of makes some kind of a cloud that's like a blob in space here. And this doesn't really tell you, so I'm not giving such a good representation of the 3 dimensions here, of course. You can't really see very well along the x1 axis when looking at the page like this. But nevertheless, like you can imagine, there is some depth to this in the x1 dimension. And the Tuki depth is defined in this interesting way where you take each point. So take this one. Oops, I didn't want to erase anything. Take this guy here or this guy here, any one point, and make a plane in the 3-dimensional space. So this is make a flat 2-dimensional surface in the 3-dimensional space, which goes through that point. Or in other words, which includes that point. Now that's not a unique plane. There are lots of planes that would do that. Let me try to draw one. So let's say I'm interested in this point here, right? It's easy. It's out of the way, so it's easy for me to draw. So like one plane that goes through it looks like this, right? And the idea is that this point is somehow in this plane. But of course, another plane that could go through it, which includes that point, might look something like, like that. And this point is in either one of those, or it's in both of those planes, or at least it's not so well drawn, I admit, but you get the idea, I hope. So I'm going to take away the plane I just drew, so we only got one there. So the Tuki depth is defined as, this is, I guess I'll put the definition, let me move this p equals 3 somewhere. All right, so the Tuki depth is the minimum number of points on one side of the hyperplane, which in this case is just a plane, through the point. So each data point, each green data point will have its own Tuki depth, and it's found by making a hyperplane here, and twirling it all around, and finding, like, based on that hyperplane, which is meant to extend through all of space, and that plane is going to cut the space in half, basically. On one side of the plane, what's the smallest number of points I can actually get on that one side of the plane? And that's called the Tuki depth. So it's a little funky, right? Now you can see that for this guy, this green one over here, I can probably make a plane that has only one point in it, which is just that green point that you see there, just this guy here. But for other places in the data set, like maybe for this guy here, it might not be possible, right? So if I draw a plane that goes through that guy, that's this point here, there's no way I can rotate that plane, possibly. to get only that one point on half the space, where the plane is the divider between the two halves. And so that point would have a larger Tuki depth, because the minimum number of points on one side of the space divided by all the planes going through that one is larger, right? So in some sense, I hope you can kind of see that, like, this guy kind of in the middle of the cloud would have like a larger Tuki depth. It's deeper into the cloud. And so the bag plot is based on that Tuki depth, and the center of the bag plot is the point of greatest Tuki depth. So the center in the plot is the point of greatest Tuki depth. And I'll just go back over there and you can see it again. And so that's this point right here, which is kind of in the middle of the cloud as it looks in the space of these two variates, but maybe it wouldn't look that way in the space of other variates. Maybe it would look less in the middle. But it's some centerness that's measured in the full 5-dimensional space here, using those, in that case, it would be 4-dimensional hyperplanes to cut the 5-dimensional space in half and twirl them around and so on. So it takes a little calculation to do it. Then there are these two different ellipses, which basically are not ellipses, but two different polygons, these nested polygons, which essentially are kind of intended to have the same purpose of the ellipses here, except defined more in terms of their Tuki depth. And so the interior polygon, or inner polygon, this one also has a name. Let's see if I can get this name right. It's called the bag. Should be able to get that one right. It contains half the data points. And I believe by the word contain here, what's meant is these points might all have similar Tuki depths, and all the points in the shaded area here have greater Tuki depths than all of the ones on the perimeter of that polygon. And it's done in this polygon is fitted in such a way that half of the data points in the data set fall into that description, fall into its interior here. And so I think that's how this guy is made. And then the next one out, so I think there's usually 3 polygons shown, or at least there sometimes are. But in this picture, you only see 2, and you see the center. And so the next one out is called the loop. The outer polygon. It's called the loop. This guy is used to define outliers. And I don't know what are the criteria for forming this guy, other than that you set some criteria, and that's your criteria for, in this case, like, so this guy is going to become an outlier. But these guys didn't, right? Each of these surfaces, I believe, is called like a convex hull in mathematical terminology. You can look at all these details if you want. Each of these perimeters of the polygons. And I'm not sure what's going on with these lines. I guess these lines are just connecting the individual points to the center. But yeah, I'm not sure why you only see them for points that are in the loop, but not inside the bag. So I'm not sure the details of that. As you can see, this one is a little complicated. I mean, anytime you're trying to project 5-dimensional information down into a 2-dimensional space and trying to make graphical understanding of it, you have sort of the potential for great power, but also for great confusion. And I think, I hope that you can understand to some extent. So this is powerful in the sense that you've properly identified the center, at least you should be able to, in some 5-dimensional sense, and you can sort of see where it actually looks, where it appears to be for these 2 different variants. Oops, sorry about that. But yeah, so let's move on from the bag plot. The bag plot, I think, is one of the more complicated, maybe the most complicated one that we had in today's, kind of schedule. The next one I'm going to go on to is called a chi plot, the chi plot. Oh, you don't need the in there, but. And I believe the origin of the name is from the Greek letter chi. Like that. I don't think this is a chi plot. And the chi plot, so, oh, sorry, I was writing on my pad and you weren't there. So the chi plot is the next thing on our list. This guy, I'm not going to say a whole lot about this. You can read more about it in the notes. But what the chi plot is used for is the following, or the notes and the book, I believe, the books. So this is useful for measuring or determining dependence, for testing independence. You know, often you'll say like these two random variables are independent and you'll move on with your life. And this plot is handy for if you have two variates, you can check to see if they actually are independent. At least that's what it's supposed to do. And I won't really say the details of it except to say that what you do is you transform like from the two variate space x2 into some new space, which is chi and lambda, and the distribution, the lambdas are supposed to obey a normal distribution. Their distances are supposed to be, the lambdas are supposed to be normalized distances from the center of a bivariate in a bivariate sense. Anyways, I didn't want to get into what exactly those transformations are because I find them a little confusing. But nevertheless, I can sort of describe for you what you're going to end up seeing. So you're going to end up with this kind of a plot. So it's going to look like a two-dimensional thing. One axis is lambda, the horizontal one, and the vertical one is chi. And there's going to be two dashed lines that are informed, that are determined by what is the expected distribution for the points. And if the data set is contained within those two dashed lines, the test is meant to indicate independence, that the two data sets are independent of each other. If you see data sets outside like this as well, or entirely, then the two variates are meant to be dependent on each other. Again, I won't say much more about them other than to say it's a good test for independence. So we'll go over there and do one. You can see how it's calculated, at least, what commands do it. And so the first thing, I'm going to plot two things. The first is just a scatter plot of these two variates, porosity and permeability. And the second one is the chi plot. So it's going to be next to it. And so here you have it. And so you should be able to make sense of this in the way I was describing. So if you look at these two things, does permeability look like it's dependent on porosity? Well, if you look over here, it seems to say that there is some dependence because most of the points are outside of the band between the two dashed lines. But does that make sense when you look at this? And I think so. I think it looks like as porosity gets larger, permeability tends to get larger as well. So yeah, that does look like there should be some dependence between those two. And so that's all I really wanted to say about the chi plot. I'm skipping some of the details of some of the things in this section of the notes, mainly because I don't have time to go over all of them, and I thought I would focus on the ones that I thought were kind of cool. The next thing I'm going to introduce is called a Trellis Plot. It goes by different names, actually. So one is called Trellis Plots. So that's one name. These tools tend not to be very old. They tend to be developed around the time of the modern computing age, so like for the 70s or newer. These are also called coplots, or I think they're also called conditioning plots. These are really simple to understand. I think in R it's really easy to produce them for both the 3D and 4D case. And so I'm going to do a 3D case. So 3 variates. And these are really simple. So the idea is the following. So 3D case is the one I'm going to be doing. Right? So the idea is that you create n different scatter plots, where n is something you can pick. In a 2-dimensional space. So you have these 3 variates, right? Let's name them x1, x2, and x3. The n different scatter plots are in the x1 and x2 space. And the x3 variable is used to decide which points actually are included. So using intervals in the 3rd variate. So maybe it's best to go ahead and make one of these and then discuss it. So I'll jump over to R and we'll make one. We're going to do the 3-dimensional case, all right? So we are going to look at 3 different variates, the permeability and porosity, which are things we've seen already. Oops, sorry. Whoa, what's happening? And then we're also going to look at conductivity. So conductivity is going to be like our x3. We're going to divide conductivity into, in this case, 2 different regions. And in this case, 3 different regions. And in this case, 4 different regions. But so let's just focus on the first one. So we cut conductivity into 2 equally sized regions. And then we plot the points that are in the 2 different regions. So let's just do it. So I've got 2 axes, permeability and porosity. There's a 0 here, so this axis repeats over here, and the labeling is put up here. And so the points on the left here were points that had conductivity in this range, 0.00698 up to 0.017. And in this one over here, the points of conductivity were in this range here. And so I think this should make it clear kind of what's happening. You're chopping up the space for the 3rd variate, and then you're taking the points from those different regions and plotting each different one on its own 2-dimensional plot. So here's where I cut the space into 3 pieces in the next line, and you get a different kind of look. And then here's where I cut the space into four regions. So this is all separating the points into different regions of conductivity, and then plotting permeability versus porosity. Okay, so that's the chi plot. I think these are really easy to understand. I'm not sure if they're super useful. Maybe they're pretty useful. At least they're super easy to understand. Like, you should be able to identify these points and see which ones they are and so on. I mean, so for example, here's one thing that's immediately apparent, right? So maybe I can go back to the very first one and you can see it. It looks like larger values of conductivity correspond to smaller values of permeability as a function of porosity. Does that carry over? It does, right? So this is the highest region of permeability, highest region of conductivity, and similar. So these 2 boxes on the top row are the highest regions again. So I don't know how useful it might be, but it's certainly a cool tool for poking around at things. The next thing I want to look at go by the name of, well, they go by various different names, but the sort of generic term for them is glyph plots. And here glyph is meant to mean some sort of a shape or symbol, and they could be, that shape or symbol could be a bubble, it could be a box, it could be more exotic things, a star, And then we'll see also faces. And it gets more elaborate. And the idea here is that, so I'll do the bubble plot first. That's one you probably actually have already done, or at least seen. So let's say you have two different variates here, x1 and x2 on the vertical. And then let's say there's a data point that's here. And then you use a third variate, x3, to determine like a radius. And you make a circle. Oh, that's a pretty badly drawn circle. A little better. Around that point with the radius x3 that's associated with that point. And then so you get different size bubbles like this. You can introduce other variates though, you can see, right? So if the radius is x3, maybe I could fill it in with a color, and maybe like the opacity of the color is determined by a fourth variate, or maybe the actual color itself, like the redness of the color, say, is determined by a fifth variate, and so on. You can make these shapes more and more complicated. The circles or bubbles, or however you want to call them, are the easiest ones, I think, to kind of describe. Bubble example. But there are more interesting ones that you can make. And so let's go and see them. They're kind of fun. So the first one I'm going to show is stars. And in this case, I believe what this is going to be is, well, let's just do it and then we'll describe it. So each one of these little shapes is a row represents a row from the data set that we're interested in, the sandstone data set. And each of these shapes has 5 lines coming out of it. So if you zoom in, you can see that a little better. Oops. All right, so there's 1, 2, 3, 4, 5. 5 lines represent the length of the different 5 lines represent the value of the 5 different variates in the 5 different columns of the data set. There's no meaning to the angle of these lines. They all come out at equally set angles, chopping a circle into so that you could make 5 lines. But it looks like there is, because so you don't see any line coming out here. But that's because this value along this axis is small, right? And so if you look at each one of these shapes represents one of the rows of the data set. And so maybe you can look at these shapes and you see some look kind of similar to each other. So like these 3 look relatively similar to each other. Certainly much closer to each other than, say, this one or this one. And so you can kind of just this is just eyeballing the rows of the matrix to see if you find any kind of interesting pattern or funny looking outliers or something like that. So this is the stars version, but there are more funny or more interesting things you can do. So the next one is called faces, and I'll just run it and then we'll discuss it. This one, instead of drawing little stars, for every single row, it draws a face, a little cartoon face. And the description of the face, which actually has 15 different descriptors here, so the height of the face, the width, structure of the face, I'm not sure what structure means, maybe that means it's more ellipsoidal or spherical, I don't know. Height of the mouth, width of the mouth, all these different things, how much smiling it's doing, all these sort of funny things, height of the ears. Each of these is informed by one of the variates. And now in our case, we only have 5 variates, and so it repeats. So permeability is associated both with the height of the face and with how much the face is smiling. So there's no new information there, and you kind of repeat 3 different times for the whole set. But anyways, you can see how it works. And the faces themselves are pretty funny. So here they are. So these faces represent the faces from our 40 different rows of the sandstone matrix. And I think it's kind of cool. You can look at this and you certainly can see, so row 35 certainly seems quite different than much of the rest of the data set. It's got these funny horn kind of things. I don't know why. You have to go back and understand the parameters that make the face and try to see what's causing that. And you should do that, I guess. But the point of this is it's a quick way to kind of identify interesting properties. And so like maybe you say like, okay, well, this guy here, he's got a different colored nose than this guy. But these 4 certainly seem kind of similar. So maybe there's some pattern. Like these guys, oh, I don't know about this. This is kind of a funny looking mouth. But like you can kind of go a little crazy with this, but it's fun, I think. And it's certainly an interesting way to kind of eyeball your data set. There's other families of faces you can do. So the default is faces, right? Faces, and then the data set. And then you can also, there's different types. I don't want to see these guys. I want to see a different collection of things. And so we'll look at those. Type 2. And the descriptors are the same. So height of nose and stuff like that. I'm not sure that they're actually exactly, I think these might be the default. This might be like the default text output. And so this might not actually be telling me anything new. Or sorry, it might not be really correct description here. I'm not sure. You should look at the sort of help files for faces and see. But in this case, the faces are these like Christmas-themed Pokemon-looking guys. They look pretty similar to the other ones, except that they have beards and Santa Claus hats. And maybe like the positioning of the star which the star is meant to represent the little like pom-pom on Santa Claus's hat. And it's positioned differently, so like here it's off to the left and here it's off to the right. I don't know what's going on. But like I said, it's a fun way to look at your data. Yeah. If nothing else, it's certainly fun. Okay, and so we'll move on now to the last thing I wanted to talk about, which is a little more sophisticated, I think, than most of the other things. And this is really... Let me think first. The stuff I'm going to introduce now is probably, these are really a bunch of things that you should be able to do in a more sophisticated way. So I'll say EDA or / graphical versions of hypothesis testing. So formal hypotheses that you might want to test, done in a kind of an informal graphical EDA style way, right? And so I'm only going to describe one of them. I'm going to describe the multivariate normality hypothesis. But there are other tests described in the notes. You can see those if you want. We may introduce those at some point if we need them. But we may not as well. And so I'm just going to focus on using quantile plots to test multivariate normality. And here normality refers to the normal distribution. And the normal distribution for multiple variables is a little bit, so we haven't really introduced it in really any detail in this module, other than in this discussion here. Maybe it'll come up later. But you can find it in the book by, I think it's Zelterman, the third book that I introduced into our repertoire of textbooks. You can find it introduced carefully there. The idea of multivariate normal data. But I just want to say for now, that multivariate normal is greater than each column being normally distributed. Each variate normal. But it does require that. It does require that each variate is normally distributed. So one quick way you can test for multivariate normality, that's sort of a one-way test in the sense that it will tell you if the data is not multivariate normal, but it won't tell you that the data is multivariate normal, is that you can do a quantile plot or something looking for normal distributions of each of the different columns. And if any of them fail, then the overall data set is not multivariate normal. But if they all pass, it doesn't tell you that the data set is multivariate normal. So that's kind of a crude, that's like maybe a quick check. Maybe it gives you confidence or something, but it doesn't necessarily tell you that the data is multivariate normal. So let's do the following. So let's say that you make, each column into, you standardize each column. So let's say that Zi, each of these is like a column. Each of these are independent, standard normal. Right, so each of these is normally distributed with zero mean and unit variance, or unit standard deviation, or variance, the same. Both of them are 1. And then you introduce y, which is the sum of the square of all those. Right, so each column of your data set you could certainly standardize, right? And then you could add the square of all of those up, and that's your variable called y. Then it turns out that y, maybe you know this already, y should be distributed, it should have a chi-squared distribution with degrees of freedom n. Right, so n is the number. Sorry, I shouldn't be using n here. I should be using p. Right, it's the number of variates that you're looking at. So this thing should have a chi-squared distribution with p degrees of freedom. And so what we want to do basically is you want to imagine for your multivariate data, to test multivariate normality, you want to basically do this. You standardize the data for each column, and then you construct this other variable that's made so you can make it for each different row of the data, where you sum up the squares of the different values of the other data, the squares of the standardized data, and then that you want to find out whether or not that thing, the y's, have a chi-squared distribution. And so to test that, you'll use a quantile plot. And so this is kind of in one dimension. So if p is equal to 1, right, then what you're doing is you're looking for a chi-squared 1 distribution, or let me write it like this. The quantity that's going to have a chi-squared 1 distribution is going to be x minus the mean squared over the variance. Right, so this quantity here, where x is the random variable, the variate, this thing should have a chi-squared distribution with 1 degree of freedom. Right? If you want to do the multivariate case, it's more complicated. If p is greater than 1, then the equivalent of this is you construct, so what's different is this quantity here. These like y's that are, you want to make something that looks like this. And so what we're going to make is the following. Right? We're going to make these things called, well, first of all, let's introduce some symbols, all right? So let's say that xi as a vector is row I of the data matrix, but stored as a column. I hope that makes sense. So you take out a row of X of the data matrix and you rotate it so that it's a column, and that's your column vector that comes from a row of the data matrix. And now mu is a column vector how do I want to write this? A column vector of means. of x's columns. Right? So the first element of mu, or the first component of mu, is the mean of the first column of the data matrix. The fourth element of mu is the mean of the fourth column of the data matrix. This guy is called a mean vector. Okay. And then the thing that we want to construct, the thing that should have a chi-squared distribution with p degrees of freedom, is the following. So we'll make this guy d sub I. So I is the row of the data matrix. So there's one for every row of the data matrix, and it looks like this. So it's xi minus the mean vector transpose, and then times the inverse of the covariance matrix. So here sigma is the covariance matrix. So this is the covariance matrix. The superscript of -1 means that it's its inverse. And then we put at the end the vector xi minus mu, not transposed. And so this whole thing is a scalar. Right? So this guy here is a length p row vector. This is a p by p matrix, and this is a length p column vector. I think I've said that right. Yeah. And so these distances, they have a funny name, Mahalanobis distance or something like that. You can look up the name in the notes. I've scribbled it down badly, but it's named after a person, I believe. But these are distances, and so these things should have. These are the distances. So this is the multivariate version of this calculation here, right? So you can kind of see what's going on here. The covariances, 1 over the variance is replaced by the inverse of the covariance matrix. And so you can see this is a matrix calculation here instead of a scalar one. It comes out as a scalar. But so this thing should have a chi-squared distribution with p degrees of freedom, right? And so if you make that calculation and collect all those d values, then you can check whether or not they have a chi-squared distribution with p degrees of freedom. And so I'm just going to now do a quick demonstration of how you actually check that. But before I do, I'm going to say there's a rule of thumb here, which I always kind of feel like I shouldn't tell you, but because nobody, like, it's, where do these things come from? Rule of thumb, trust it only if you kind of have a lot of data points, like if you have the rows outnumber the columns by a factor of 10. Right, that's a rule of thumb, so I don't know. You can trust it if you want to or not. And remember, this is just a way to do a graphical test using a quantile plot for something that you might be more wise to do a formal hypothesis test of. But this is a quick thing, or at least it's a little quicker, and you can just check it really fast. So you compute these d's and then do a quantile plot. So I'll jump over here and make the quantile plot, but I'm actually going to kind of cheat. I'm only going to do it in the case where p is equal to 1. So it's really just univariate. And so really, I'm really just doing this version of the thing. I should probably code up a version where we do it for multivariate, but the idea is just to demonstrate how to do a quantile plot once you get here, right? And so let's go over there to R, and we'll finish this lecture with this example. So this is using quantile plots to check the chi-square, the expected chi-square distributions. So we're going to make 5,000 samples of 3 different distributions. So this one is a chi-square distribution with 1 degree of freedom. This guy is a log normal distribution. And the next one we're going to make is called x3. And it's built using this function here. All right, so we're going to have x1, x2, and x3. And this function here so this distribution is called a log Cauchy. We don't really need to talk about it. It's just yet another distribution that is not chi-squared with 1 degree of freedom. And so this guy makes x3. x2 is made from these two rows, right? So first you get the sample of the log normal, and then you standardize it, right? So we're subtracting off the mean and divided by the standard deviation squared, or the variance. So these guys, if they were sampled from a chi-squared distribution, they would be chi-squared distributed, but they're not. Or sorry, if they were sampled from a normal distribution, then this thing would be chi-squared distributed. These distances would be, but these are not. And then at this bottom thing, what we're going to do is we're going to extract here the quantile positions for a chi-squared normal distribution with 1 degree of freedom. So I'm going to run this, and then we're going to make a quantile plot, QQ plot, 3 different ones, comparing the expected thing, the chi-squared with 1 degree of freedom, to x1. All right, so these are actually these are the same, but x1, it's a different sampling, so it's not exactly the same. So we're checking if the distributions are the same, and this should look like a straight line. And then we'll make a quantile plot for x2, and it probably won't be a straight line, and this also won't be, I think. So let's run it and see. Yeah, so here are the 3 different things. So this is x1, this is the one we expected to be a straight line, and it's pretty close to a straight line. And again, this is crude, right? They're just doing these visual things, indicating that these are so-called multivariate normal, although these were only univariate. This guy is not a very straight line, so this guy looks pretty bad, not multivariate normal, or not normal. And this guy, you can't really see what's happening here because so much of it is down here near 0, but that's because the scale is totally blown up by this outlier, which is at 8 times 10 to the 281. So you can't even see the structure here, but you can see that this thing is way, 10 to the 281. What is that? That's a bizarro kind of number. So this guy's out, and this one is in, which is what you would expect. All right, I hope you enjoyed trying out some exploratory data analysis, and I hope you enjoyed the sort of dual form of lecture, half computational, half whiteboard, iPad, mathematical writing stuff. I hope that worked out for you. All right, I'll see you next time.